Hi everyone, we are back and we're going to be solving equations using linear algebra. So here I've got a 4x4 matrix. Let's do matrix form. And here we go. We can look at the determinant. Determinant is non-zero, so we can start to solve problems because we're going to have to use the inverse in a little bit. So we will only have, again, a unique solution if my determinant of my matrix is non-zero, hence why we calculate right there. So I've got my matrix, but this matrix effectively can represent this system of equations, or at least these kind of factors here. So I could, if I have these four equations, I can write this in matrix form. So my A matrix will just be the coefficients of these variables, x, y, z, and t. And then I could find and actually define a vector. My solution to this, these equations are going to be B. So my B vector will just be 10, minus 17, 18, and 14. And then I'm asking, what are the conditions of x, which are going to be a vector again, or a first rank tensor effectively. Let me see, x1. So I need to make sure I clear x1. I need to define a vector effectively that will give me the solutions. So what are my values for x, y, z, and t that lead to this solution? So this is kind of your fundamental, the most important equation that you'll ever really kind of get in touch or basically play around with in linear algebra. So we are going to use this relationship to solve our system of equations. So let's go ahead and get to it. So I've got x1, I've got b, so I could do a dot x. And if I pull it out, again, this looks like my equation above. But just in terms of, I could have solved this in x, y, and z, but the problem is I have this x here, and then I want to make sure that we're okay. So I can solve this equation directly. So if I do a dot x equals b, it solves for my unknowns. I can also do a function called linear solve. So linear solve is actually pretty cool. Linear solve will basically say, okay, you've given me a matrix, you've given me a b, find an x that gives me the solution. So it's essentially the same thing, except instead of x1 goes to, it gives you essentially those values directly. So again, it gives in that order that you set it up. Now, one of the important properties is you can treat this linear algebra expression, similar to how we do kind of algebra, and hence, linear algebra. So let's say I wanted to solve for x as well directly. What I could do, knowing that, I have a and I have b. Well, I could rearrange my function, right? So I could basically multiply any matrix times its inverse of itself should be equal to 1. So it's basically like dividing it, right? A to the minus 1 power. Now we don't want to write it that way because, so for example, if I do inverse of a, let's look at this. So first let's look at a matrix form. Let's do inverse of a matrix form. And let's do a to the minus 1 matrix form. So very different, actually, what am I doing here? Very, very, very different values, right? So what is the inverse doing? Inverse of a square matrix. So again, you kind of see how we're doing and how we're calculating essentially those values. So you're looking at and you're calculating, and you can see here in symbolic form, we're looking at the inverse values of this matrix. So it is not this a to the minus 1 power. So the inverse is a distinct value. So we need to make sure again, and that we have to make sure that we're able to essentially calculate the inverse. If my determinant, for example, m1, if I try to do the inverse of m1, doesn't work. And if I got to do the inverse of m2, actually, where's it? Hang on a second, let me clear. Let me clear quickly B. So I want to look at m2. I want to do the inverse m2, and you can see how it's calculated effectively. So you can look at and calculate essentially that inverse. But anyways, let me reevaluate B. So what we're looking at, taking the inverse, is very, very, very different. So I can't do that now because it's dead. But so if I don't have a determinant, I cannot take the inverse. So that's clear in here. That's my determinant. We can actually do, sorry, let me clear B one more time. We could actually look at determinant of M2. And you can see, we're basically dividing out by the determinant, and then we're doing those inverse operations. But anyways, those are kind of matrix operations. Hopefully you've seen those before. But anyways, I can go ahead and start to solve this function using kind of this type of expression. So I could do, just multiply out. Inverse A dot A will give me B. Actually, I need to put an A here. Inverse A dot A, X. So I could do here. And you can see I'll get those values. Again, just same property, right? So if I do an inverse of A dot A, that will give me what's called basically an identity matrix. So let's do matrix form. So this is an identity matrix. I could also do an identity matrix of 4. I could do an identity matrix. 4 is going to be the rank of my, or actually the, basically a 3 by 3, a 2 by 2, 1. I could do 10, 15, those are all good, good stuff. But anyways, those are essentially the values that you're going to find, for this identity matrix. So if I inverse A, I get that value back, which makes sense. That's what we're saying essentially in this first function here. But I could also solve for the value of X, which will be equal to the inverse A dot B. And when I do that, this is the same solutions as we did with solve here. So you can solve these problems in very similar ways. And this is one of the beautiful parts of linear algebra. It's that we can solve equations in multiple ways and actually, figure it out. So what happens when our determinant is 0? So I get this, I solve, again, there are no solutions here. Singular, if I look at all these values, it doesn't work. So what's happening, one of our 4 equations is a linear combination of the other equations. So we have 3 equations and we're asking it to solve for 4 unknowns. And you can actually confirm that by looking at the rank of the matrix, which is, so I look at rank of my matrix 0. So it tells me essentially how many, basically independent, the number of linear combinations. So 4 equations, basically one of them is a combination of the other one. So you could see and actually look at the rank of the matrix or the linear independent equations. So we only have 2 independent equations. So that's a big problem here. We're trying to solve for this one. So determinant is 0, that's a problem. And then we could also kind of look at that in the matrix. So unfortunately, when that happens, we're not going to be able to solve for it because we're asking for the impossible. So we're asking to solve for 4 unknowns, but we only have 3 equations. So, excellent. Now, next time we'll get into eigenvalues and eigenvectors. See you next time. Thanks. Bye.